Welcome everybody back, I hope, for today's lecture. Let's go ahead and continue our discussion on capacitors, and specifically I'd like to do a plotting example for today. Plotting is going to be important to us in that it will be definitely a question on the final exam that will be coming up here before we know it. So let's go ahead and get started, and let's build a circuit. So we'll keep the circuit pretty straightforward. We'll go ahead and do again a little exercise, perhaps on mesh and nodal analysis again. So let's create a little circuit here, and this will be our circuit. And again, if we're going to analyze a capacitive circuit, we have two steps. We have a Thevenin analysis and we have a Norton analysis to do. Why? Because we need to find the max voltage and we need to find the max available current to that capacitor. The capacitor is modeled as two parallel plates with an open in between them. And so Thevenin wise, we need to model this circuit as an open here at this point. In other words, find the open circuit voltage or the Thevenin voltage. And then we also need to be able to model the maximum current to the plates. The current does not go through this space, but the current builds by pulling electrons off one side of the plate and stacking them on the plate on the other side of the capacitor. So let's go ahead and start with the Thevenin analysis. And since we're looking for a voltage, that typically means we want to look at the nodes. And so identify the nodes. We've got one here starting, and then again we model this as an open here. So if this is an open, since we're doing Thevenin voltage, we ask the question, is there a current occurring through here? The answer to that is no. If there's no current, there is no voltage across this resistance or that resistor. So essentially this just becomes a wire. So we will treat it as one node. Then we have a node here across the bottom. And for convenience sakes, I'm going to assume that this is the 0 volt node, and this one up here is V1. So we're going to sum the currents to find voltages. Start here at this node and work our way to the left, subtracting any voltages between this node and that node and dividing by any resistances along that wire. So we have V1 minus 10 minus 0 here at the next node divided by 3. Take this wire, so we have V1 minus this node down here over 6. We got this wire going down to the lower right, so that's V1 minus 0 over 5. And then we've already discussed how there is no current through this wire. It's just all part of the node, so we ignore that, and all those currents will sum up to 0. Get our terms collected together. That takes care of that V1, that V1, that V1. We have a minus 10 over 3. And that takes care of all of our terms. Everything else is a 0. And those currents sum up to 0. And so we get a V1 here. And let me get to my calculator fired up. And that's 0.7. Go ahead and pull this to the other side. and that becomes a positive 10/3, which is about a 3.333. And so don't need to set up a matrix for this, just one simple equation with one unknown. Just divide both sides by that 0.7, and we get a voltage here of about we'll call it 4.8 volts. And so we have 0 volts on this side, we have V1 on that side, and V1 is 4.8, so our Thevenin voltage is simply V1, which is 4.8 volts. Okay, so we have our Thevenin voltage. Well, we want to go ahead and drive our Norton current now. And so for the Norton, typically we want to do mesh. So we have our circuit here. Here's a circuit loop, call it I1, and here's another loop over here. Whoops, not paying attention. We got another one here, we'll call I2. Then one over here we'll call I3, because we have this wire going through there. I almost forgot that I did that. So we sum voltages to find a current. So we sum voltages for loop 1. We've got an I1 times 3 plus 6 minus I2 times 6 minus I3 times 0, because I3 does not touch that loop here on the left. It's isolated from it. We have a minus 10 volts. Take that to the other side, and it becomes a positive 10 volts. So we have one equation. Sum the voltages for the second mesh loop, which is this one right in here. Go minus I1 times 6 plus I2 times 6 and 5, which is 11, minus I3 times that 5 ohms. And there's no voltage source in there, so it's just equal to 0. And then let's sum the voltages for I3. I1 does not touch it, so it's just 0. I2 times 5 plus I3 times, and since we're shorting that, so we have a 5 and a 2, which makes 7. No voltage source there, so that's a 0. And since we have 3 equations, the easiest method to deal with that is to use a matrix. So we have our I1, I2, I3, and we have a 6, a minus 6, and a 0. We have a 10 there. Then we have a minus 6, and 11, a minus 5, 0, 0, minus 5, 7, and 0. So we will put this system into our calculating machine, and hopefully we can all get the same answer. Let's see, we have a 3 by 3, and so the first term is 6, then we have a negative 6, 0, and negative 6, 11, negative 5, 0, negative 5, 7. I did it pretty quickly, so I'll verify my numbers. That looks good. And we'll go to my 3 by 1 vector. We got a 10, a 0, and a 0. And then we'll call the matrices up, and I'll find the inverse of the 3 by 3. Call up the vector, multiply them, and we get about 8.7 amps, 7 amps, and 5 amps. That's kind of unusual to come up with nice round numbers like that. But what we're looking for is I Norton. So we go back and look at our circuit. I realize it's kind of a mess here, but we're looking at this current right here through that closed loop, and it's in this loop here. So we have I3 circulating out there, so I Norton in this case is simply I3, which is equal to 5 amps. So we've got our Norton current and we have our Thevenin voltage, so that gives us the opportunity to find that Thevenin resistance, which would be our voltage, which is 4.8 volts divided by 5 amps, and we're going to see here our resistance is not very high. Looks like about 0.96 ohms. And since we're dealing with a capacitor, we want to go ahead and find that time constant, tau, which is R Thevenin times C. I did not give a value for C, so I should probably go ahead and do that. Let's make C equal to, let's choose something different from yesterday, 0.47 microfarads. That's a very common size for a capacitor. And so the tau will be 0.96 ohms times 0.47 microfarads. And so tau comes out to be looks like 0.451 microseconds. Yes, ohms times farads gives us seconds. And so we've got our Thevenin voltage, we have our Norton current, we have our Thevenin, which enabled us to find our tau time constant of 0.451 microseconds. Now I said we need to do some plotting. Okay, so I'm going to show you the easiest way to do plotting. Okay, I'm going to build a table of values. First one is going to be time, and we'll just call that tau since that's the time constant we're using. We need our voltage value for the capacitor. Now we need the current value for the capacitor. And let's review real quickly what the equations are. The equations for the voltage of a capacitor is the Thevenin voltage times the quantity 1 minus e to the minus tau. For the current of the capacitor is equal to the Norton current times e to the minus tau. And so I've got to answer my phone real quick, so hold on. Sorry about that, I received a phone call I had to answer. Okay, here we are. Here are our two equations, one for voltage, one for current. And so let's go ahead and determine our voltages. And we're going to use tau for that time constant up here. And this is the easy way to do it. Just say 1 tau, 2 tau, 3 tau, 4 tau, 5 tau. And now let's run the equations. Okay, so here we go. Let's do the voltages first. So our Thevenin voltage is 4.8 volts. So we got that. Then we have a 1, so I'll go ahead and enter that. Then we have a minus e to the minus tau. Well, here I've got an e to the x button. Whoops. So what happened here? Well, I did e to the x and it just took what was on my stack, so I need to go ahead and delete that off. And so go ahead and enter it. So what I need to do is I need to enter the value for tau, which is going to be minus 1. Then I hit the e to the x button and I get a complex number. So hold on a second here, I've got to reset my calculator mode. Sorry again for the interruption. Sorry for that interruption. This is my new calculator and I briefly forgot how to do the e to the x function, even though it should have been pretty easy. Okay, so here we go. Again, our Thevenin voltage is 4.8. Once we have the Thevenin voltage, then we got a 1, enter, and then I'm going to raise e to the minus tau, and tau is just going to be 1. So e to the minus 1, so I enter the minus 1, and then I hit the e to the x button. Then I've got to subtract that from 1, and then multiply it, and we get 3.034. So I'm just going to call it 3.03 volts. And let's go to the next one. Again, we have our 4.8 volts. Get the 1 in there, and then get the not. Then we have a 2 tau, but minus 2 tau. So go ahead and enter that minus 2 and hit the e to the x button. Subtract that from 1, multiply it times 4.8, and we get 4.15. So I'll call it 4.2. And then we have our 4.8 volts again. And we're going to do minus to the minus 3 power. Subtract that from 1, multiply it, and we get 4.56, so I'll call it 4.6. Again, the 4.8 volts, and then we've got our minus 4 tau, so that's minus 4, hit the e to the x button, subtract that from 1, multiply it, and we get 4.712, so I'll call it 4.7. And then we're at 5 tau. So 4.8 volts, and 5 to the minus sign, raise that e to the x, subtract that, multiply it, and we get 4.768. So that's like 4.78. Close enough. Didn't come up exactly 4.8, but we're getting, as we can see, we're approaching 4.8. So at minus 5 tau, we're approaching that 4.8 voltage value. The more time constants we add, the closer we'll get to that 4.8. We just say, you know, at 5 time constants, we're about 98% of the way there. So that got us our voltage values. So now, hopefully I can do this a little more smoothly. Let's do our current for various time constants 1, 2, 3, 4, 5. And now it's just our Norton current, which is 5 amps. And then we have e to the minus time constant. So do that first one and just multiply it, and we get 1.8, about 1.84 amps. This is going to be a fairly large capacitor. It's physically sized, even though the farad value isn't terribly large, but to handle that kind of current, we're going to have a physically large capacitor. Just for a little segue. Okay, so again we have our current, which is 5 amps, and then we have the second time constant. That gives us about 0.68 amps. And then we have our third time constant, voltages. This is about 0.25 amps. Our fourth time constant gives us 0.018 amps. And then for the fifth time constant, we get 0.003 amps basically. So we're definitely approaching zero. Not quite to zero yet, but getting there. Okay, so that's I need to move the decimal point. That should be there. That makes more sense to me. So this should be 0.18. I need to do a better job of reading my calculator. 0.03 amps. Okay, so we now have some numerical values, and now we can plot our response curves for voltage and current for a capacitor. I just like to go ahead and use my engineering paper if you want. I mean, obviously you can use full-fledged graphing paper, but this serves our purpose for now. I'd like to go ahead and just use a straight edge of some kind, and since we are actually plotting and not sketching this time, sketching just means I just freehand it. Plotting means something a little bit more precise. And so let's go ahead and do our voltage of the capacitor versus time. And obviously we're going to start out at 0 volts and 0 time, and we need to go up to 4.8 volts. And so probably should have thought a little bit better ahead of time, but I like to use about 4 or 5 divisions per volt. So there's 1, 2, 3, 4. That's 1, 1, 2, 3, 4, 2, 1, 2, 3, 4, 3, 1, 2, 3, 4, 4. I didn't do a very good job, so I'm going to have to do about 2 spaces per division. So this be 1, 2, 3, 4, 5 volts. And then we have 5 time constants. So I want to, let's see if we do 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5. Well, got a little bit better here. This is 1 tau, 2 tau, 3 tau, 4 tau, and 5 tau. These are units of time in seconds, where each tau is 0.451 microseconds. Okay, at time 0, we are at 0 volts. At time 5 tau, we're at 4.8 volts. So I'll go up here, and that's 5 volts, so 4.8 to be right in here somewhere. And then at 1 tau, we're at 3.03 volts, so I'm just going to put it right there. 2 tau, we're at 4.2 volts, so a little bit more above that line. 3 tau, we're at 4.6 volts, so something like that. And then at 4 tau, we're at 4.7 volts, so not quite as high as the point there, but getting close. And so there's a drawing tool called a French curve. I don't know where I put it right now, so I'll just go ahead and just freehand the curve just to help highlight it. But if I say plot, you don't even really have to draw the curve. You should just put the points there. And so here we have an exponential curve, and we should label it V sub c versus tau. So there we've plotted our voltage curve for this capacitor over 5 time constants. And then we can do the same thing for current. For time, the current of the capacitor. And again, 4 worked well for the time constants. So that's 1 tau, 1, 2, 3, 4, 2 tau, 1, 2, 3, 4, 3 tau, 4 tau, and 5 tau. Okay, and then our current goes from about 1.84 amps down to 0.03. So obviously this will be 0 amps, and that will be 0 time, and that will be in amps. And so I can do a little bit different spacing there. So I'm going to call each one of these a 0.1. See if that was a 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6. So here's 2 amps. Here's 1 amp. Each spacing is going to be 0.1 amps. So 1.84. That puts us here at 1.8. That's 1.9, so not quite halfway up. That's our initial starting current, about 1.84 amps. Then at one time constant, we drop all the way down to 0.68. So 0.1, 2, 3, 4, 5, 6, 7 there. So right around in here. Then at 2 tau, we're at 0.25. So that's right there. At 3 tau, we're, excuse me, at 1 tau, we're, oh, excuse me. I'm going to do this current over. I was misreading my table here. I should have put a 0 line in my table. So, sorry about that. Let's try this again. We're going to plot current versus time. Our starting initial value was the Norton current, not the current at 1 tau. My mistake. So the Norton current starts off at 5 amps. So I'm going to go ahead and do the taus again. This is where using a pencil instead of a pen would have been helpful, but okay, we need to go up to 5 amps. So let's see, 1, 2, 3, 4. I can do this. This is 0, 1 amp, 2, 3, 4, 5 amps. Label that, and it's time. So at time 0, we started off at 5 amps. At time 1 tau, we're at 1.84. So that's 2, 4, 6, 8. So a little bit up there. And at 2 tau, we're at 0.68. 2, 4, 6, 7, right around there. 3 tau, 0.25. So something like that. 4 tau, 0.18. So getting close there and just above the line right there. So we've got, you know, an exponential curve dropping something like that. Again, I would not freehand this normally. I would use a drawing instrument to help me get that curve. I'll have to chase down my curve, French curve drawing instrument, and I can show you how to use that next time. But that was all I really wanted to cover today, was just some basic plotting for the capacitor for voltage and current. And again, I would rather you just plot the points and not draw the curve if you don't have a curve drawing instrument. Or you could use Excel if you wanted to plug those values into your columns in Excel and tell Excel to plot it for you. But this will give you an idea of what a plot should look like for the capacitor for voltage and current. Until next time, hopefully you're doing well on your homework. Make sure you email me with any questions. We can always Zoom conference if you want to have face-to-face time with me. But otherwise, stay healthy.